Let's discuss Unit 8 solutions. Consider the following finite automata F1 that accepts a language L. They have given the transition diagram. Let F2 be a finite automata which is obtained by reversal of F1. Then which of the following is correct? In the reversal of an automata, all the transitions will be preserved. Let's take the reversal automata. The final state becomes the initial state here, and the initial state becomes the final state, and the states in between will be in the reversal order. Here there is only one state, so we are just placing it between the initial and the final state. We have to check whether all the transitions can be applied in the reversal automata too. So there is a transition from C to S, there is a transition from S to E, there is a transition from C to E. So this one, they are preserved. Then we have E to S, S to C and E to C. So E to S, S to C and E to C. Now we have preserved all these transitions. So now they are asking whether the language generated by F1 and language generated by F2 will be equal or will not be equal or will be the subset of the another. So we have to find this. Since all the transitions are preserved in this automata, we can say that the language generated by F1 will be equal to the language generated by F2. So option number 2 will be the right answer. When I have the same set of transitions in F1 and F2, obviously the language generated by both the automata will be same. Next question, which of the following statement is correct? Let's start with the first statement. Ackermann's function is primitive recursive. First, let's understand what is primitive recursive function. It's a function computed by a program whose loops are all for loops. It means the upper bound of the number of iterations can be determined before entering the loop. Just we'll have the structure. Before entering the body of the loop, we will know how many iterations it has to go. So during every increment or during every iteration, we'll be knowing what is the upper bound. But if you take the case of while loop or do while loop, this condition will be checked here and the increment of the condition will happen here. So only in for loop this will be possible. So this is called as primitive recursive function. Let me give you the Ackermann's function and then tell you whether it is primitive recursive or not. This is represented by a of m comma n. There are three conditions here. If m is equal to 0, it is n plus 1. If m is greater than 0 and n is equal to 0, it will return m minus 1 comma 1. So it's a recursive function. There is no doubt with this format, but we have to check whether it is primitive recursive. If m is greater than 0 and n is greater than 0, the call will be m minus 1 a of m comma n minus 1. When you want to represent factorial problem or Fibonacci problem in terms of recursion, we use this format. In primitive, they say that all the loops will be for loops. But here in Ackermann function, to implement this, we will use while loops and not for loops. Taking this to be the reason, we say that Ackermann's function is not primitive recursive. So 1 is not correct. The second statement is the language a power n, b power k, c power n plus k, n greater than or equal to 0, k greater than or equal to 0 is regular. So to check whether a language is regular or not, we have to go with the pumping lemma. I'm not going to explain pumping lemma here. Instead, I will just list the rules of pumping lemma. So let us take a string w. It will be in the form of x, y, z. And we have to check three rules here. The first one is the length of y should be greater than 0. It should not be equal to 0. The second condition will be when you take the length of x and y, it should be less than or equal to m. So m is a constant that will be assigning a value. The third one is x y power I z should also be in the language for all I greater than or equal to 0. So even when the y part is missing for y power 0, the string should be in the language. Let's take m is equal to 3 for the purpose of pumping lemma. Now let's find the strings available in the language first. So n is equal to 0, k is equal to 0. This will give a power 0, b power 0 and c power 0. So L will have empty string. Then for n is equal to 0 and k is equal to 1. B and c. So BC, k is equal to 0 and n is equal to 1. We'll have AC. Just substitute in the language and find it out. Let's take n is equal to 1 and k is equal to 1. A will have a power 1, b will have b power 1, c will have c power 2. So A, B, C, C. When you have n is equal to 3 and k is equal to 3, we'll have triple A, triple B and 6 number of C's. The count of number of A's and the count of number of B's. When you add them together, it will be the count of number of C's. By pumping lemma, we can express this language in the form of a power m, b power m and c power 2 into m. So m plus m will give you 2m. We have already taken the value of m to be 3. Now let's take the longest string here. The condition will state that we have to select the string that will be greater than or equal to m. W is equal to triple A, triple B, triple C 2 times. Okay, now I have to split it as x, y and z. How should I split this x, y, z? When you take the count of x and y together, it should be less than or equal to m. So here m's value will be 3. So I can take 3 characters together to be x and y. Now I can split this xy as a for x and a for y, or it can be a for x and double a for y. For the third rule, when you eliminate one y stating y power 0, so they say I is greater than or equal to 0. So it can be x into y power 0 into z. So let's take this case. It is double A and y power 0 means this A will be missing. Then you will have triple B and 6 C's together. Is this string in the language? No, it is not. Similarly, you can take this to be the case. For x, y power 0 is z. I can have x here and I can eliminate this y in the name of y power 0. Then I will have triple p and 6 number of c's. Is this in the language? No, it is not. When this x into y power I into z for all I greater than or equal to 0 is not in L, it means the language is not regular. So this is not a regular language. And moreover, when you try to represent this in the form of regular expression, you can express A as A star, B as B star, and for C, you cannot say the number of counts. So here the condition of the expression will be like when you add the number of A's and number of B's, you should get the number of C's. But in regular expression, you cannot express that. You can also think this way to say that this is not a regular language. The conclusion will be option number 2 is also wrong. Now let's check option number 3. They have given a language and they have told this is not context free language. So this is a power n, b power j and n is equal to j square. By pumping lemma, let's take the string w to be in the form of u, v, x, y, z. So let's take the language to be in the form of a power m square into b power m. So we have to express it using the same variable here. Here also we will take the value of m to be 3. Now let's see the conditions that has to be checked. First condition will be the length of Vy should be greater than or equal to 1. The length of Vxy, the center part, excluding u and z, it has to be less than or equal to m. And the third one, will be u v par I x y par I z should also be in the language for all I greater than or equal to 0. Here let's take sample strings of the language. So for n is equal to 3, j is equal to 9. So you will have 9 A's, 1, 2, 3, 4, 5, 6, 7, 8, 9, and you will have 3 B's. This will be the string that we are going to work out. So let me place 9 A's and 3 B's. Now I have to choose such that Vxy will be less than or equal to 3. Some 3 A's will be chosen. In that case, if I take V par I, Y par I as 0. So if I is equal to 0, I have to eliminate 2 A's here. When I eliminate 2 A's here, there will be only 7 A's remaining in the string. Is this string in the language? No, it is not. With this case, we can conclude that this language is not context free, and this statement is the correct statement. So option 3 will be the right answer. So obviously now we will know option 4 is also wrong, but we will just see what is wrong with that. For every context sensitive language L, not including lambda, there exists some linear bounded automata, that is LBA M, such that they have given L not equal to L of M, but this is actually L is equal to L of M. This will be the right statement. They have also said if a language L is accepted by linear bounded automata M, then there exists a context sensitive grammar that generates L. So this statement is also supporting L is equal to L of M. Since they have given it is not equal to, we are marking this also to be wrong statement. So from this we can say the language A par n B par j, where n is equal to j square, is not context free language. This is the only right statement out of these 4 options. Next question. The maximum yield length of the following CNF CFG. So CNF is Chomsky normal form and CFG is context free grammar. They have given some productions here. Yield is a terminal string represented as W. The value of W will be less than or equal to 2 par n minus 1. N is the height of the longest path in tree. Now let's take S. When I do this derivation, S has A, B non-terminals. Then A has C, D as non-terminals. I can have E here because B is producing E, and C will have A and D will have B here. This is the yield. This yield has 3 terminals, but based on the height we have to tell the maximum yield length. Height 0, height 1, height 2, height 3. So n will be equal to 3. Let me substitute n here, 3 minus 1. So this will be 2 par 2 and this will give 4. The maximum yield length of the following CFG will be option number 3, 4. So the tree is nothing but the past tree here. Next question. Consider the following language. W belongs to A, B, C closure. Number of A's in the string plus number of B's in the string will give number of C's in the string. So let's first understand what is linear. A language generated by a linear grammar is linear language. In linear grammar, each production has at most one non-terminal. At most in the sense it will be less than or equal to 1. So every production doesn't have the non-terminal, or it will have only one non-terminal, not more than that. So non-terminals are usually represented by capital letters and terminals are represented by small letters. And there is also another point. Any linear grammar is context free, but not all context free are linear, because when you have more than one non-terminal, it doesn't fall under linear grammar. Now we have to check whether the particular language is context free and then we'll check for linearity. So here they have given the number of A's and number of B's. When they are added together, it should give number of C's. So let's, for example, take 2 number of A's and 2 number of B's and end up with 4 number of C's. So you have 2 A's, 2 B's. When you add 2 plus 2, it will give you 4. So this is number of A and this is number of B, and 4 will be the number of C. This is what is given here. How can I convert this into a context-free grammar? First, we have to understand one thing. Whenever there is a, there should be a C. Whenever there is a B, there should be a C. Only then this condition can be satisfied. So for every A accompanied by C, I can generate a rule AC. For every B accompanied by C, I can have BC. Now when I write it in the form of grammar, I can just write S derives ASC BSC. Since it is given in the form of closure, it doesn't mean that I have to go with this order. I can also go in any order. So for that purpose, for ASC, I can also write it to be CSA. I mean, C can also have one A and C can also have one B. So CSB. This doesn't give you any order due to the closure symbol. At the same time, since star is used, it means there can be no string also. So in that case, I can also include epsilon here to indicate that there is no production. Actually, for producing ASC or CSA, there are two ways to derive AC or CA. Similarly, when I have BSC and CSB, this is to derive BC and CB. So there are two ways of deriving it. So the grammar has epsilon for the smallest string. Similarly, we are introducing SS. For one possibility it will be 1S, and for the other possibility you will have other S. So I can also include SS. I have to rearrange this grammar properly. SS, ASC, CSA, BSC, CSB and epsilon. Both the versions are right, but whenever you write, you should always start with non-terminals together and then end up with null string. That will be good. This is actually context free. Just check whether you are able to derive the strings. So S will give SS, then this will give ASC and this will give BSC. Now I am just giving null value here and this will end up with ACBC. Just count the number A plus B. This is also 1, this is also 1 and there are 2 C's. So this is satisfying the condition given here. We are not worried about the order. We are only worried about the count of C, whether it is equivalent to the sum of A and B. Okay. And this can also have a derivation like SS. This can be ASC, this can be epsilon, and this can be ABSCC. This will end up with epsilon. So the final string will be ABCC. This will also give 1A, 1B and 2C. Different kinds of derivation, but the rule number of A plus number of B is equal to number of C is the main thing here. So from this we can say that the language is context free language. It means not context free and linear will be ruled out. Now we have to check whether it is linear or not. In linear grammar, I have already told the production should have at most one non-terminal. It means it can either have one non-terminal or it need not have any non-terminal. But here if you take, there are two non-terminals SS. So violating this rule, we can say this language is not linear. In this case, we are marking option number 1, context free but not linear, to be the right answer. Option 3 is also ruled out. So to check for linearity, you have to check the number of non-terminals. They have only one non-terminal, they are fine. There are no non-terminals, this is also fine. But here there are two non-terminals, which is against this rule. Next question. The compiler for high-level language that runs on one machine and produces code for the other machine is called. When you see the definition of cross compiler is capable of creating executable code for a platform other than the one on which the compiler is running. This states that it runs on one machine and produces codes for the other machine. So from this statement we can understand option number 1, cross compiler, will be the right answer. An example of cross compiler will be a compiler running on PC. It will generate code that runs on Android phone. Now what is multipass compiler? So this will process the source code of a program several times. It means it will have several passes. What is optimizing compiler? This will try to minimize or maximize some attributes of an executable computer program. The reason for doing this is it will optimize the compilation process. What is one pass compiler? This will process the input exactly once. That is one pass. So cross compiler will be the right answer for this question. Next question, which of the following parser is most powerful parser? Already we have discussed in one question paper about the order of complexity among the parsers. So let me give you that order. Canonical LR, which is called as CLR, is more powerful than LALR, look ahead, which is greater than SLR, and this is greater than LR of 0. So this will be SLR of 1 and this will be LALR of 1. And what is canonical LR? It is LR of 1. This will be the order. So in this we have to understand what is operator precedence parser. It is a bottom up parser that interprets on operator grammar. They also say it's a shift reduced parser, and this parser will be a subset of LR1 grammars. In any way, canonical LR is the most powerful parser. Option number 3 will be the right answer. Next question. Which phase of compiler checks the grammar of programming? What does it do in code optimization? This will transform code in a more efficient way without changing the output. What is semantic analysis? This will check if the language constructs are meaningful and also whether the language constructs are consistent with the language definition. What are code generators? They convert intermediate code to machine code. This code will be executed by the target system. What is syntax analysis? If you take the compiler phases, it will start from lexical analysis and then move to syntax analysis. This syntax analysis phase takes a stream of tokens from lexical analysis phase and checks whether they comply with the grammar of the programming language. Which phase of compiler checks the grammar of programming? It is syntax analysis phase. Option 4 will be the right answer. Next question. Given below are two statements. If f and g are two functions and f is equal to O of g and g is equal to O of f, we say that the growth rate of g is smaller than that of f. For the same statement, the actual growth rate of g is greater than that of f, not smaller. We have seen proofs related to this in Unit 7 regarding asymptotically positive functions. We have already seen. So let me give you a small reminder. So if f is equal to big O of g, this means that f is less than or equal to some constant into g of n. F is smaller than g here. In this case, if you take O of g of n, asymptotically grows no faster than g of n. We can say f of n also grows no faster than g of n. When I say f cannot go above g, the growth rate of g will be greater than f. But the statement given here is g will be smaller than f. So this statement is false. The second one, the class of all decision problems decided by a Turing machine in exponential time, that is big O of 2 power k being a constant. This part is wrong. What is the right thing? All decision problems are solvable by Turing machine in exponential time, and the time will be big O of 2 power p of n. So what is p of n? It is polynomial function of n. You can also express this like big O of 2 power n power k. Taking this into consideration, we are marking statement 2 also to be false. So option number 2, both statement 1 and statement 2 are incorrect. Next question. They have given 4 statements and they are asking us to choose the correct answer from the options given below. The set of Turing machine codes for Turing machine that accept all inputs that are palindromes, that is possible along with some other inputs, is decidable. The set of codes for TM to accept all inputs that are palindromes is not decidable. So they say it is undecidable problem. A is false. Remove the options that have A. The next statement. The language of codes for Turing machines M that when started with blank tape eventually write a 1 somewhere on the tape is undecidable. This is actually true. All these statements you can find in theory of automata books or articles regarding that. The third one, the language accepted by a Turing machine M is L of M, and this is always recursive. Here I would like to add some details. The language accepted by the Turing machine M is recursively enumerable, denoted by RE. Recursively enumerable will have recursive inside it, and inside recursive we will have CFL, and inside CFL we will have regular. But if you want the language to be accepted by the Turing machine, then it should be recursively enumerable. Then what about recursive? The subset of recursively enumerable language accepted by the Turing machine that always halts are called recursive. When you get a scenario where the Turing machine halts, then it is recursive because this is going to be a subset of the recursively enumerable part. But when it has to be accepted by TM, then it has to be recursively enumerable. When it accepts, it is recursively enumerable. When it recognizes the language and the Turing machine halts, then it is recursive. So this statement, the language accepted by the Turing machine is always recursive, is false. Next statement, post correspondence problem is undecidable. This is also true. Once you find C to be false, you can take out 3 options from the right answer. So option number 4, B and D only will be the right answer. Next question. This question has no key. Consider the following statements. A context-free language is generated by LR grammar if and only if it is accepted by a deterministic push-down automata called as DPDA and has prefix property. What is prefix property? If a string W is in L, no prefix of W is in L. When you add some prefix to the string W, this new string added with the prefix should not be a part of the language. That is prefix property. Now there are statements like context-free languages are accepted by PDA. Language accepted by DPDA must obey prefix property. This point ensures this part is true. And this statement continues like this language accepted by DPDA with empty stack must obey prefix property. This is actually same as the language generated by the LR of 0 grammar, which is stating this part to be true. To support this part generated by LR of 0 if and only if it is accepted by DPDA, we have one more statement. Every deterministic context-free language DCFL can be parsed by LR of 0 grammar. So we can mark A to be true. Next statement, if M1 is the single tape Turing machine simulating multi-tape Turing machine, then the time taken by M1 to simulate n moves is n power 3. It is not n power 3. The time taken by M1 to simulate n moves is big O of n square. So B will be false. Automatically we can remove three options. But A has to be included in the answer set. None of the four options are having A and excluding B. And here they have given option 3 as C and D only, but we already know A is true. So this is also not there. That's why no key has been declared. Next statement. Push-down automata behaves like a Turing machine when it has one auxiliary memory. The supporting statement for C will be a push-down automata or PDA if contains more than one stack. Usually PDA will be implemented by a stack. That's why they have given if it contains more than one stack, and this more than one stack can be taken as the auxiliary memory. When it has two stacks, the second stack will be the auxiliary memory. Then it is a Turing machine. So this statement is also true. The next statement, L is equal to A par n, B par n, C par n greater than or equal to 1 is not CFL but context sensitive. Let's take n is equal to 3. Triple A, triple B, triple C. As per the pumping lemma, let's take the string to be U, V, X, Y, Z. So we have to check for this. So if V, X, Y contains only A's, so only from the A part we are choosing V, X, Y. According to the third rule from the pumping lemma of CFL, we have V par I, X, Y par I, where I greater than or equal to 0. So in this case, when I mark I is equal to 0, from the number of A's, I will be removing at least 2 A's. Then A's count will not be equal to B's count and C's count. Once A becomes less than the number of B's and C's, that is not a valid string generated by the language. So the language is not context free is true. So you can also take another way. If Vxy contains only B's, so when I is equal to 0, the B's count will be lesser than the count of A's and C's. So this also is not a part of the language. So not context free is right. But we have to check whether it is context sensitive. Context sensitive language will be generated by the context sensitive grammar. So what is context sensitive grammar? It's an unrestricted grammar in which productions are of the form alpha derives beta, where alpha length will be less than or equal to the length of beta. And what are alpha and beta? Alpha and beta are strings of terminals and non-terminals. Restricted grammar will be in regular language, but as you go higher, it will become unrestricted. What can you understand from alpha, beta are strings of terminals and non-terminals? It means the left hand side will have a combination of terminals and non-terminals, and the right hand side will also have a combination of terminals and non-terminals. S derives A, S, B, C or A, B, C. Then we have C, B derives B, C. Then we have B, B derives B, B. Two stacks will be needed for this grammar. Just the previous statement we have seen PDA with one more stack, that is when it has one auxiliary memory, it behaves like TM. So we can construct Turing machine for this language. When you have a combination of terminals and non-terminals both in the left hand side and right hand side of the production, then we can call it to be context sensitive grammar. What grammar is this? This is the grammar of the given language. Though we may say we can construct Turing machine for that, but for context sensitive language we have a term called linear bounded automata. And the linear bound automata is nothing but it is a non-deterministic Turing machine. See, usually in Turing machine you will have both the ends open, but in linear bounded automata the ends will be bounded. That's why it is called so. linear bounded, and you cannot have a very lengthy input due to the bound present. So that is the difference between linear bounded automata and Turing machine. This is the context sensitive grammar for the given language A parent, B parent and C parent. So the statement D, the language is not context free but context sensitive, is also true. So the right answers will be A, C and D. All these three statements are true. This will be the right answer for this question. With this, we are completing Unit 8 questions.